no icon for recording here. Can any of you see any recording on your tab? Recording tab. Huh?
No, sir.
No recording, right? So let me see. Okay, so that's why I don't like using this Meet. Okay, anyway, I think maybe we'll see what we'll do in the next class. Maybe we'll use a different, what do you call it, different source. Okay, so I'm sharing my slide now. So, okay, Bismillah ar-Rahman ar-Rahim, Alhamdulillah Rabbil Alameen, Ar-Rahman ar-Rahim, Maliki Yawmiddin. إياك نعبد وإياك نستعين اهدنا الصراط المستقيم صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين آمين لا الذي لا يضر مع اسمه شيء في الأرض ولا في السماء وهو السميع العليم اللهم إني أسألك كلمة نافعة ورزقا طيبا وعملا متقبلا اللهم ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار صلى الله على سيدنا محمد نبي أمي وعلى آله وصحبه أجمعين الحمد لله رب العالمين. Yes, so we have already started our discussion on this chapter. So I think maybe better I should show my video on my webcam. Let me see. Okay. So, okay. 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 So share my slide. So is the slide showing? Hello?
No, doctor.
No slide, sir.
No slide.
Yes, no slide.
No slide, sir.
Mm, can you see my slide now?
Yes, Doctor.
Okay. So I think I did stop somewhere here. Okay, we have discussed this question, right? Okay. Okay, so I think we have been, I don't know why there is echo. Let's see. Okay, let's try. Let's see. Oh, I don't know why there is echo in my voice. So is it clear to you, my voice?
Clear, Doctor.
Huh?
Clear.
I can't
It's
hear
clear,
you
Doctor.
properly.
No problem, sir.
Okay, okay. All right. So I'm going to discuss about turbulent and laminar flow. Okay. In the previous class, we discussed about the Reynolds number. And Reynolds number is a parameter which is used to identify the flow situation in a particular flow field. Okay. So we can have completely turbulent flow situation or a mix of laminar and turbulent. You understand? So now here, we have fluid flowing across a flat plate. And across the entire plate, the flow is turbulent. Whereas for this particular figure, we can see that there is a laminar flow up to a certain distance, after which there is turbulence. You understand? So now this X is what we refer to as X critical. That is the critical length, after which the fluid changes to turbulent flow. Okay? So, and the turbulence flow can be depicted by this particular figure. You can see that and these figures are lined up in a straight line. We have 2, 5, 7. So take these lines to be, let's say, free streams of a fluid. But looking at this particular situation, the figures are mixed up, means that the fluid molecules are mixed up over here. So this is the situation for turbulence, okay? So we say the intense mixing in turbulent flow brings fluid particles at different temperatures into close contact and thus enhances heat transfer. Now, we're gonna discuss about film temperature. Fluid temperature at the surface, Ts. Let's say I have a solid surface like this and fluid flowing across it. Okay. So if the temperature of the fluid is T infinity and temperature of the surface is Ts, film temperature is defined as Ts plus T infinity divided by 2. Okay? It is this value of Tf that we are going to use to identify or find the density of the fluid, the Prandtl number, the dynamic viscosity, kinematic viscosity, and so on. So now there is, for every laminar flow, there is appropriate equation for the velocity boundary layer, which is given by this. And similarly, for a turbulent flow, the velocity boundary layer is given by this. So whenever you have a question where the fluid is turbulent and you are asked to determine the velocity boundary layer, then you need to use this equation. The same thing applies to skin friction coefficient. Okay? And for a laminar flow across a flat plate where the Reynolds number is less than the critical Reynolds number, the appropriate equation for the skin friction coefficient is given by this. And similarly, for a turbulent flow, okay, the skin friction coefficient is also given by this equation. So we can see here that the Reynolds number is greater than the critical Reynolds number, but less than 10 raised to the power of 7. And similar information, okay, can be seen over here. For a Prandtl number greater than 0.6, the Nusselt number is given by this equation. Okay, so we have Nu, this is a local Nusselt number, equals to Hx divided by K. And this same equation equals to this. Okay. So now for a turbulent flow situation, the Nusselt number is quite different. You see that these equations are similar to some extent. Okay, so this can be used in both cases. But for a specific turbulent flow, this is the governing equation for a fluid flow across a flat plate where we have the Prandtl normal greater than 0.6 but less than 60, and the Reynolds number greater than the critical Reynolds number but less than 10 raised to the power 7. All right. So now, these are the equations that are or can be applied for a turbulent flow. Okay. So for this particular condition, the appropriate Nusselt number to be used is given by this. All right. And then for a mixed flow means that we have, let's say, across a flat plate like this, and up to a certain portion of the plate, the flow is laminar. And after which, the flow becomes turbulent. So this is what we call a mixed flow situation. For a mixed flow situation, the appropriate equation to determine the Nusselt number is given by this. Okay? And this condition also has to be fulfilled. So now let's look at this example. So in this example, we have oil flows over 40 meters long heated pipe at free stream conditions of 5 meters per second and 25 degrees Celsius. If the plate is held at 45 degrees Celsius, okay, determine the velocity and thermal boundary layer. Okay, thermal boundary layer thickness at the middle of the plate. So first thing over here, we need to find TF. Okay. After we have been able to find TF, then we need to find the Reynolds number. Reynolds number will help us to identify the flow situation, whether it is laminar flow or turbulent flow. Okay. And then we have to calculate the distance where the laminar changes to turbulent flow. So means we need to find X critical. Okay. And then the last portion, calculate the total convection heat transfer for 1 meter's width of the plate. So like you have seen, the film temperature is given by 35. So it is based on this temperature that we will select our Prandtl number, kinematic viscosity, thermal conductivity, and density of the fluid. Okay? And at the middle portion of the plate, so we have the plate like this. Okay. The whole length of the plate is L equals to 40. So, but we have been asked to calculate the thermal boundary layer, the velocity boundary layer and thermal boundary layer at the point half of the plate. So we need to find out what is the flow situation. Is it laminar flow or turbulent? Okay. So now we calculate, we know the velocity of the fluid, X now equals to 20, and the kinematic viscosity we know already. So now this gives us 2.86 times 10 raised to the power 5. So now we see that this value is greater than the critical Reynolds number. Okay? So the flow at the midpoint of the plate is laminar flow. Okay? Oh, sorry. I made a mistake here. Let me see. Yes, the critical Reynolds number is 5 times 10 raised to the power 5. And here we have, let's say, 2. So it's less than the critical Reynolds number. Yes, so that's it. Then the flow across the plate up to half portion of the plate is given by laminar flow. Okay, so based on this laminar flow, then we are going to use the appropriate equation for the velocity boundary layer, okay, which is given by this. So 5 times 20 divided by square root of the Reynolds number. And so that gives us this. So 18.76, sorry, 18.7 centimeters. And the thermal boundary layer is also given by this equation, all right? So if you substitute the velocity boundary layer here, the Prandtl number, then you get the thermal boundary layer to be this. Okay? So we can observe one thing, that if you sketch both on a flat plate, the thermal boundary layer is quite lower than the velocity boundary layer. Okay, so the thermal boundary layer covers up to this point, whereas the velocity boundary layer is much greater. Okay, so that is the physical implication of these two results. Now, we want to determine the rate of heat transfer. See, the question says, calculate the distance where the laminar changes to turbulent flow. Okay, so we will calculate the velocity across the entire plate. Okay, so this is 5.714 times 10 raised to the power 5. So now we see that the flow across the entire plate is turbulent. Okay, because this result is greater than the critical Reynolds number. All right. So now the critical distance or transition point from laminar to turbulent is given by this equation. Okay, so here we have X critical equals to R critical. Then we have the kinematic viscosity divided by the velocity. Okay, so now be careful. So R critical is an equation which is a function of the velocity of the fluid times the X critical divided by kinematic viscosity. So when you are asked to find the point where there is a transition from laminar to turbulent flow, then means they want you to find X critical. So X critical is 35. So it means that across the plate like this, we will have, if the whole plate is 40, okay, and it means that up to the point, let's say X equals to 35, the flow is laminar. Okay, then it means the other portion is turbulent flow. So it means that across the entire plate, the flow is mixed flow. Okay, so it's a mixed flow situation. So if it's a mixed flow situation, then we need to use the Nonson number for a mixed flow. Okay, so when we adopt this equation to determine the Nonson number for a mixed flow, the Nonson number results in this. So based on this information, we are now going to find the heat transfer coefficient. So heat transfer coefficient is given by NuHL divided by K. All right. So now we will have the notion H equals to Nu times K divided by L. So eventually we'll have the heat transfer coefficient to be 68.7. So it is this value that we are going to use to calculate the heat transfer, which is HA times delta T. Okay. So now you see, so the total heat transfer across the plate is given by this. Very easy. Okay, so now let us look at flow across a cylinder. So far we have identified flow across a flat surface. Okay, now you want to see what are the conditions for flow across a cylinder. Now, the general equation based on Churchill and Bernstein developed this empirical equation for flow over a cylinder. So whenever you have a cylinder and you want to find the Nusselt number, then you need to use this equation. But bear in mind that we initially define Nu equals to HL divided by K. So here because we are talking about cylinder, the L becomes D. Okay, so whenever you have cylinder and you want to calculate the Nusselt number, feel free to use D. Okay. And then Whittaker also developed this empirical equation for flow over a sphere. So this is for a cylinder. And then we have for a sphere. Okay. So now these are various empirical results which people have been presented related to the Nusselt number based on different range of Reynolds number. For a Reynolds number between 0.4 up to 4 for a circular object, then the appropriate Nusselt number is this. And similarly, for 4 up to 40, the appropriate Nusselt number is. So based on the Nusselt number, the Reynolds number that you calculate, you have to use that to identify the appropriate Nusselt number. And for a square, for a gas, okay, the range of Reynolds number, and its corresponding Nusselt number is given by this. For a square tilted, these are the appropriate equations. And for hexagon, okay, with a Reynolds number within this range, then appropriate Nusselt number is this. Okay, hexagon tilted. Okay, so these are the fundamental equation. For a vertical plate, the Nusselt number is this. For ellipse geometry, the Nusselt number is this. Okay, so now let us look at this example. So here we are told that a long 10 centimeters diameter steam pipe whose external surface temperature is 110 degrees Celsius passes through some open area. Okay, so it means air is flowing across the pipe. That is not protected against the wind. Determine the rate of heat loss from the pipe per unit length when the air is at 1 atmospheric pressure and 10 degrees Celsius, and the wind is blowing across the pipe at a velocity of 8 meters per second. Okay, so here also One thing you need to calculate TF. Okay. Also, we need to find the Reynolds number. And based on this Reynolds number, we will select the appropriate Nonson number equation. Okay. Okay, so let's see. Okay, so I'm going to solve this question later on. Okay. Now, let us look at this question. We are told that a long 10 centimeters diameter hexagonal steam pipe whose external surface temperature is 110, okay, passes through some open area that is not protected against the wind. Determine the rate of heat loss when the air is at 1 atmosphere pressure and 10 degrees Celsius, and the wind is blowing across 1 meter length pipe at a velocity of 8 meters per second. Basically, it is similar to this particular question. Okay, the difference is that this is hexagon. Okay, so now, as usual, we will calculate the thermal film temperature, right? Then after that, we will use this to identify the Prandtl number, thermal conductivity, kinematic viscosity, and so on. So now we will determine the Reynolds number. The Reynolds number is given by VD divided by kinematic viscosity, which is given by this. So the Nelson number can be determined from table 7.1 in the textbook. So if you go into the textbook, you'll find, according to this Reynolds number, for hexagon, the appropriate Reynolds number is this. So let's see whether we have it here for hexagon. So the Reynolds number we got was 4.219 times 10 raised to the power of 4. So that gives us 2190. Okay, 42,000. Okay, now if we go back, okay. So for hexagon, here we have 5,000, between 5,000 and 100,000. Okay, the Nelson number is there. So you see that we have 42,000. So 42,000 is within this range. You understand? So the appropriate Nelson number to use is this. Okay. Yes, so this is the equation. So when you calculate the Nelson number is given by this. And then from here we can find the heat transfer coefficient. And after you got that, that's the heat transfer coefficient. So now we need to find the heat transfer. We know Q equals to HA delta T. Okay, now we need to identify the area. How do we find the area of the hexagon? The area of the hexagon equals to 6 times the diameter of the hexagon divided by 2 sine 60 times L. Okay, so if you take the hexagon to be, let's say, of length this. Okay, so in order to find this particular width, so if you know the angle, this angle, okay, and then the diameter of the hexagon or the radius this distance is d over 2 because the whole length is d. So if you cut into 2, it becomes d over 2. So if I know this height and I'm interested in this width, okay, then it's gonna be sine, and let's say sine 60 equals to opposite, okay, over adjacent. So let's say the adjacent is given by x. So that gives us d over 2 divided by x, okay? So now we'll have x equals to d divided by 2 divided by sine 60. So eventually this becomes x equals to d divided by 2 sine 60. Okay, and that's what we have over here. All right, so it means that we have found this x. Then if you multiply by the length, that gives you the area. You understand me? But we have 6 sides. 1, 2, 3, 4, 5, 6. So that's why I multiply by 6. So that's the total area of the hexagon. So Q equals to HA TS minus T infinity, which is given by. Okay. All right. So I think I'll be proceeding with this in the next class. Okay. In the meantime, I'll take about 5-minute break and then we'll solve some few questions before leaving. Hello? Can you hear me? Can you see the slide?
Yes, sir.
All right. So I have a question over here that I want us to discuss. This is past year question, 2019. Okay. In this question, we are told that by using an example, describe the significance of thermal conductivity of a material in heat transfer. Okay, so you need to explain and say that thermal conductivity of a material is a measure of how fast heat will be conducted in the material. Okay, so example is very poor conductors, okay, have low thermal conductivity. Okay, and then we move on to this question. The question is, consider a large plane wall. So we have a large plane wall in this question with a surface area of 5 meters square. Okay. And the thickness is L equals to 0.2 centimeters. That's the thickness. And then we have, let's see. So the thermal conductivity equals to 2.0. The left side of the wall is maintained at constant temperature, T equals to 30. Okay, so that's the left side. While the right side loses heat by convection to the surrounding at T equals to 0 degrees Celsius with a heat transfer coefficient of H equals to 40. Assuming constant thermal conductivity and no heat generation in the wall, express the differential equation and the boundary condition for steady state one-dimensional heat conduction. Okay, so here what we are supposed to do is to write down the general equation for three-dimensional heat conduction in a rectangular object. So like I always tell you, you can just flip down to this section and copy this. Okay, you can copy this one, this equation. Okay, 1 over alpha dt over dt, and then you continue from there. You understand? Yes, so it is this equation we are going to use. Okay? we have the square t over the x squared plus the square t over the y squared plus the square t over the z squared plus q. That's the heat generation divided by k. Okay, so based on the question now, let's go back. Okay, so we have, this is our geometry. Now the boundary, the assumptions that is given in the question is like this. We have steady state, condition, and then one-dimensional heat conduction, okay? And no heat generation. So this 1, 2, and 3 conditions are very important. So based on this condition, we will cancel this. This is steady state condition, 2-dimension. This will be 0, this will be 0, and there is no heat generation. Okay, so now we'll be left with the square t over the x squared equals to 0. So what are we supposed to do next? Now we need to apply, integration. So if I integrate this function with respect to x, so this gives me dt over the dx equals to c1, right? So again, we integrate again. So this gives me, you can rearrange like this and say that this is dt equals to c1 times dx. So if I integrate this, this gives me tx equals to c1 times x plus what? c2. Okay? So now from here, we need to apply boundary condition. Boundary. Okay? So now, what are the boundary conditions that are given? At the point where x equals to 0, so at x equals to 0, what is t? Okay, t equals to, let's say, let's look at a diagram. So at x equals to 0, t equals to t1, and this equals to 30 degrees Celsius. Let me sketch the diagram here. Okay, so here we have T1 equals to 30 degrees Celsius, and T infinity equals to 0 degrees Celsius. H equals to 40, right? The thickness L equals to 0.2 meters. Okay, so now, based on this boundary condition, at x equals to 0, t equals to 30. So the function is t of x equals to c1 times x plus c2. At x equals to 0, so we have t1 is equal to 30 equals to C1 times 0 plus C2. So C2 equals to 30. Okay, so now we will apply another boundary condition. So we don't know the temperature on this surface. See, the solid is like this. The temperature here is known, T1. But the temperature here, let's say T2, we don't know. We only know T infinity and H means air is flowing across the surface. Okay? So you cannot say that, let's say at X equals to L, okay? T equals to T2. We don't know the value for T2. You understand? So we can apply constant heat flux at this surface. Constant heat flux at X equals to L. Okay? So if you apply constant heat flux, we can say that at X equals to L, okay, so we have Q conduction equals to Q convection. All right, so Q conduction at that particular surface, X equals to L, equals to minus K, okay, dt over L. Okay, so now we can mention that this also equals to, so for Q convection is given by H T infinity okay, so, and there's a mistake here. It should be H into bracket T2 minus T infinity, like this. Okay, so we are going to equate these two equations together. So now this is gonna give us minus K. Now this T, delta T is given by T2 minus T1, okay, divided by L. And this equals to H T2 minus T1, sorry, minus T infinity, like this. Or better still, I think the appropriate thing to do over here, maybe, let me delete this. So this may not be able to work out. Maybe I'm going to draw it in a different place. Okay, so I have, this is T1, and then T2, I have T infinity over here. So now I'm going to apply sorry. So at X equals to L, we have Q conduction equals to Q convection. Okay, so now Q conduction equals to minus K dt over the X, whereas Q convection equals to H delta T. In other words, T2 minus T infinity. Okay, so we know the T over the X in this equation. The T over the X equals to C1. Okay, so whenever I see dt over the X, I replace by C1. All right, so eventually we'll have minus K dt over the X equals to H T2 minus T infinity. Okay, so now minus C1 equals to, sorry, K C1 equals to H T2 minus T infinity. So eventually C1 equals to H T2 minus T infinity divided by K. Okay, so now I'm going to substitute my values for C1 and C2. C2 is 30 and C1 is given by this equation. Okay, so now we have T as a function of X equals to C1 X plus C2. So now we're gonna have minus H T2 minus T infinity divided by K plus 30. Okay, so, oh sorry, times X over here. All right, so this is the equation. This is governing the heat transfer. Okay, so now let's look at the next question. So now, sorry, we have been able to obtain a relation of the variation of temperature in the world by solving the differential equation. Now, evaluate the rate of heat transfer through the wall. Okay, so we want to determine the rate of heat transfer through the wall. So now this gives me Q equals to minus Ka dt over dx. Okay. And this will be equal to minus Ka times C1. C1 we know to be equal to the whole of this. All right. So now this gives me minus Ka then times H T2 minus T infinity divided by the thermal conductivity. Okay. Okay. So now you only need to substitute the parameters for K. Okay. Oh yes, here K will cancel K here. And then you need to substitute the value for H, the area, T2, and T infinity. So you need to calculate this. You can do this yourself at home. Okay. Yes, so maybe we can look at this question as well. Now the question says that describe three parameters which determine the heat transfer coefficient of convection between a solid surface and moving fluid. What are the three parameters which determine the heat transfer coefficient of convection? Okay, so you see here, in other words, they want you to elaborate the dependence of the heat transfer coefficient on its hydrodynamic properties, okay, such as the fluid properties. So I've told you last time that if, so now we are solving question 2A. In not heat transfer due to convection is given by HA Ts minus T infinity, where H equals to overall heat transfer coefficient. All right. So this heat transfer coefficient is not a property of the material across which the heat is flowing. Okay. So here we have fluid flowing across a hot surface. This H is a parameter which it depends on one, fluid properties. Depends on the fluid property. Means the density, the viscosity of the fluid, either dynamic viscosity or kinematic viscosity, or the thermal conductivity. So when these parameters are changing, then the value of H will also be changing. Similarly, this H depends on the type of flow. So means that when the flow is laminar or turbulent, the flow will be different, or the value of H will be different. And number three, H also depends on the solid geometry. I've told you that, let's say, if you have a triangular object, you have a circular object, you have a flat plate, and then fluid is flowing across all of them. Each and every one will have different H. The heat transfer coefficient for number one will be different from number two, will be different from number three. You understand? So this H depends on the geometry across which the fluid is flowing. And then lastly, number four, surface condition. Surface condition. It means it depends also on the surface roughness. For a smooth surface, the value for H will be different. For a rough surface, the value for H will also be different. Okay. Now, moving back to the next question, we have a steel pipe is delivering hot water from a cogeneration plant to a nearby stadium for underground pitching, heating to prepare a football match during winter. The pipe, whose external surface temperature is 95 degrees Celsius, passes through some open area that is not protected against the wind. The ambient temperature is 5 degrees Celsius, and the wind flows with a velocity of 8 meters per second, crossing over the pipe. Given the pipe's diameter as 15 centimeters, determine the rate of heat loss per unit length from the external surface of the pipe by convection. So here we are giving giving the various range of Reynolds number and the appropriate Nusselt number. You understand? So very important thing, we need to calculate first RE. Okay? And RE we know equals to U times D divided by kinematic viscosity. Okay? So how do we determine this kinematic viscosity? We need to find TF. Okay? So this TF will give us the thermal conductivity of the fluid, the kinematic viscosity, the density, and so on. Okay. So in this situation, let's say this is the pipeline. Okay. We have the pipeline like this. The surface temperature of the pipe is 90 degrees Celsius. Okay, so let's say it equals Ts. And ambient temperature So the ambient temperature is 5 degrees Celsius. So T, so means air is flowing across it. And T infinity equals to 5 degrees Celsius. Five degrees Celsius. So from here, we can calculate TF equals to 95 plus 5 divided by 2, which is equal to 100. Oh, sorry, 50 degrees Celsius. Okay, so based on this information, we need to go to the table that is given. So from here, who can suggest which column we should take? Yes, anybody? The one with 50, right?
Oh, yes.
Yes. So please be careful all the time. So the one with 50, this. So we know the density, the thermal conductivity, kinematic viscosity, dynamic viscosity, kinematic viscosity, and Prandtl. So this is what you are supposed to use. If you mistakenly use 90, because the temperature of the pipe is 90, then it will be wrong. Okay, so you should be careful. If you take 100, also it is wrong. All right. All right, so now let's calculate our Reynolds number. Reynolds number equals to UD divided by, kinematic viscosity, which is equals to 8 times 0.15 divided by 1.798 times 10 raised to the power minus 5. So this gives me 66740. Okay. So now, based on this, we will select the appropriate Nusselt number. Let's see. 66740. Okay. So here we have 66740. 66740. So looking at this situation, which one should we take? So this is 66,000. 66,000. So this is 40,000. We cannot use that. So the appropriate one is what? This one, right? So we need to use this to calculate the Nusselt number. So means use this one. This is what we're going to use. Okay, I hope everybody is following. These type of questions are very easy. So now, based on this, I'll have my NU equals to 0.027 times RE 0.805 times PR 110. Okay, so if you calculate this, it will give you 0.027 times 66740 raised to the power 805. Okay, times 0.7 1/3. And this equals to 185.35. Okay, so that is NU. So based on this information now, we know the general formula for NU equals to HD divided by what? K. So now H equals to NU times K divided by diameter. So the diameter of the area of the cylinder equals to, we'll have H, calculate H first. H equals to the Nusselt number 0.02735 times 185.53, all divided by 0.15. Okay, so the diameter is 0.15. This equals to 33.80 watts, okay, Kelvin per meter squared. So now we need to calculate Q equals to HA T S minus T infinite. So now the area equals to pi DL. Okay. So now we substitute. So Q will be equal to 3,380 by 95 minus 5. Okay, so this gives me 1433.3 watts per meters. Okay, so it means watt per length. Okay, so this gives us the final answer. Okay, so I think it's almost 6 o'clock, so we will stop at this point and then we'll continue again in the next class. So far, is there any question from anybody? Hello?
No, sir.
All right. So then hope to see you in the next upper week. So next week is a mid-semester break, right?
Yes, sir.
All right. So have a nice holiday. Assalamu alaikum.
Thank you.